Now, before we get into the main part of the theory itself, let's remind ourselves of some important pieces about orbitals and start building up to the point where we end up inside of the theory. Now, suppose we have an s orbital and a p orbital, and we're getting those things close enough together that they can start to bond. What we're going to say is that the s and the p orbitals are going to end up mixing together. Thing is, they're going to make a new orbital, and that new orbital is going to be repelling other electrons, just like we talked about in VSEPR. So the fact that these orbitals are now overlapping is going to be one of our bonds. The rest of them are going to have to spread out to give that newly formed bond some space. And that's going to give us our three-dimensional structure. Now we're going to use the fact that it's an s orbital and a p orbital mixing in order to give us the notation that we're going to use. Now suppose that we take an s orbital and one p orbital, and we throw those both in the blender together. That's the phrasing I'm going to use for it. Well, keep in mind that on that atom, we had an s orbital. We had three p orbitals. There's one, there's two, and then there's the ones going in and out of the paper. That's three. So we'll have an s and three p orbitals. We only took one of the s's and one of the p's, and we mixed them. Well, let me give you a disgusting example to make this stick in your mind. Suppose that we take one cherry and one anchovy, and we throw those both in the blender, and we turn it on. We're going to end up having two volumes to pour out. The volume of our original cherry, the volume of the fish together, and then divide it into two portions. Each of them are going to taste half like cherry and half like anchovy, which will be a totally disgusting mix. But we're going to have, I don't know, a cherry fish. And it's going to taste pretty nasty. And we're going to have two of those. And we're going to have the other two, we'll say cherries, left over. We'll assume that the p orbitals were cherries. In other words, the new orbitals with s flavor and p flavor are now going to have a 50-50 mix of s orbital characteristics and p orbital characteristics. The other two p orbitals are going to be totally left alone. And so if we were to actually stop talking about fishes and cherries, we're going to have one of these mixed portions. So we'll have one of these s and p combinations here. We'll have one of these s and p combinations over here. We'll have our p orbital. Notice that there's a total of 2 electrons in it. So that's a p orbital. And here's our other p orbital. And these sp orbitals each have 2 electrons because they are a standalone, complete orbital that can hold 2 electrons. So if we have an sp hybrid, this is what we're going to end up having. Now let me get rid of the ink for a second. Notice though, whenever we drew bonds, we said a bond was a region of space where 2 electrons were really localized. Here's another region of space where 2 electrons are really localized. Notice that these are going to be 2 bonds that are spread out at 180 degrees in a straight line. We can start to see the basis of some geometry starting to happen. Now the parts that are missing are going to be the bonds and things that we talked about in the previous chapter, previous section of this chapter. But we'll mix that in here in just a minute. Let's consider the next case of hybridization though. Now in this one we're going to take one s orbital, my anchovy, and 2 cherries. We're going to throw them in the blender. It's still going to taste disgusting. It's still going to taste like anchovy and like cherry. It's just going to taste more like cherry. I'm not sure that that's any better. So these sp2 hybrids are going to result when we take an s orbital and 2 p orbitals, mix them in our blender together, and leave the remaining p orbital totally alone. We're going to get a total of 3 orbitals because we had a portion of s orbital, we had 2 portions of p, so we have a total of 3 portions when we pour them back out. Each portion just tastes like anchovy and cherry at the same time. It's going to have a third s characteristic, 2/3 p characteristic, with a total of 3 of these bonding orbitals. And our p orbital that we never messed with remains pointing up and down. And wow, look at that! A bond laying 120 degrees away from another bond, and in a plane with a third 120-degree bond. This is looking a lot like our trigonal planar geometries before. Totally different way of getting there, but it's giving us some of the same results. Now if we were to take all of those orbitals, our s and 3 p orbitals, and throw them in the blender together, it's going to taste more like a p orbital than it did before, and a little bit less like a s orbital. But we're still taking a total of 4 orbitals in, which means we still have to spit a total of 4 orbitals out. It's just that each of these orbitals will taste a quarter like s and 3/4 like p. And so we'll have those 4, they'll be spaced out in 3 dimensions, and it'll look like a tetrahedral geometry. And so that's the basic idea behind mixing these things and getting our hybridization notations.